It's a familiar sound.
So this week, we're very happy to have Marek Biskup to tell us about exceptional points of planar random walks.
All right, thank you so much. It's a pleasure to give a talk at UBC again. What you deprived me of is the actual trip, which I always enjoyed very much, even though we've had some rain here in Los Angeles as well, so not too bad. So I would like to tell you about work, which is, I will tell you the parts which are done, for which the actual paper is out, but the work is still ongoing. And there are interesting connections that I will mention at the very end. At this point, there are two papers. One is with Yoshihiro Abe from Chiba University, and the other one includes also Sangchul Ali, who was my former graduate student and who, well, is spending the pandemic teaching at UCLA right now because somehow the jobs didn't materialize for him at the moment when he needed them. Okay, so I will start with some motivation, and that goes back quite a while ago. So Erdős and Taylor in 1960 put up a paper, which is actually published in a slightly obscure journal. It's in the Hungarian Academy of Science, I believe, where they basically asked the following question: if you consider a simple random walk on Z2, so the two-dimensional case is the interesting one for this question, and you let it run for time order n, and you count for each site in Z2 how many times it has been visited. So the question is, what's the largest time you will see? So what's the most popular point as far as the visits of the random walk are concerned? Okay, and they ask this question and they provide some first level answer to this. So here is some setting. So I will write xn for the simple random walk. I will always start it at 0, at least for the purpose of this discussion. Write ln x for the number of times the random walk has visited a vertex x. That includes 0, but that's not really so important. Up to time n in here. And then the theorem that Erdős and Taylor proved is that there exist positive constants such that the maximum local time is bounded between two multiples of log n squared. And these multiples are positive. And in fact, the constant C2 is the constant that you have on the right-hand side here. So this problem lay untouched for close to 40 years, well, probably like 37 or 38, until Amir Dembo, Yuval Perez, Jay Rosen, and Ofer Zaytouni put up a very influential and important paper in 2000, well, published in 2001 in Acta Mathematica, in which they actually showed that if normalized by the log n squared, the maximum local time in fact converges to a limit, and that limit is in the normalization of the local time that I have here is 4 over, oh, actually, that's a typo. There should not be a squared. I apologize, 4 over pi. Okay.
You have ZD there, Marek. Do you mean Z2?
Yeah, I said, did I? Yeah, I mean Z2, yes. Did I?
Well, you wrote
yeah,
ZD, so
yeah,
D is 2.
So D is equal to 2 in the entire talk.
Okay.
It's only for 2D. So maybe I should say a little bit more that this 4 over pi that has to do with the behavior of the green function. I apologize, somebody's. So this 4 over pi, maybe I'll actually just use the tools to correct my typos. And I will work in red. Okay, so there's 4 over. Can you hear me? Hello?
Now we can.
Fine.
Yeah. Somebody called my phone, and that on a Mac now seems to want to start the music program, which shuts my my headphones off, and I have no idea why. Okay, so D equals 2 in this talk. Okay, D equals 2. So this 4 over pi has to do with the behavior, with the asymptotic behavior of the green function, and of course such a theorem will be true in other dimensions as well. But the value is interesting and the proof is less interesting, and the proof is more difficult. In that case, of course, you don't normalize by log n squared. In that case, you normalize just by the actually by log n squared as well. Okay. All right. So let me not worry about other dimensions, so that I don't say things which are wrong, because I have not thought about this in a long time. So the question is, on this paper, is that can we get beyond the leading order, and can we understand the limit row? Okay. All right, so here's more motivation that I want to. So there's another paper by the same authors from 2006, in which they look actually at the simple random walk on a torus of size n, now two-dimensional, and they defined what they call late points. Actually, don't like that name. I'll explain why. But they defined late points as such that have not been visited by time theta times 4/pi n log n squared. Okay. So theta is a parameter in this game, which you can take in principle any positive number. But then they proved is that if you take theta larger than 1, then are in fact no late points. So this should be an empty set, really. I mean, the number of late points is 0. And if you take theta between 0 and 1, then there is in fact a leading order asymptotics, at least at the level of exponent limit, to the number, and they have the sort of this fractional power of the volume type of asymptotics. Okay, and the O1 tends to 0 in probability. And again, the same question persists. Can we understand this number beyond the leading order, and is there in fact a limit law for this? Okay, so I put up some simulations for you to actually see what happens with the two-dimensional random walk, because they inevitably come out very nice and fractal, and that's really the feature of the two-dimensional random walk. So this is a run of a random walk started from the origin. On the left-hand side, what you see is the set of visited points. So this is this kind of nice fractal structure. And on the right-hand side, what you see is the local time profile. And so you see that actually quite a few of these high values, and they kind of tend to spread regardless of where you are. There's clearly some kind of a fractal underlying structure. Okay, here's a little bit more of simulations. Let's see if this actually loads. Yes, I think that I picked files which are a little too large. So this is actually not this is for a random walk which keeps coming back to the domain. It's not for the torus, and I'll explain the return mechanism. But for the time being, you can think of this as just basically taking a torus and running the random walk for a theta multiple of n squared log n squared times a magic constant, which is the 4/pi, and then you plot the set of points which have not been visited when theta is equal 0.1, and when theta is 0.3, and then of course this is for the same run of the random walk. So we see that some of the structure that was not visited remains, but others have already been wiped out, and so on. And as theta increases, this will become thinner and thinner, and when theta hits 1, you lose all points together. Okay, so the bottom line of these simulations is that we should expect some fractal structure from the spatial distribution of these points. Okay, so what I'm gonna show you is actually a slightly different problem than the one in the second paper I quoted. It's the one where we do not run the random walk on a torus, but we actually run it in a scaled up version of a nice continuous domain in R2. Again, this is 2. Okay, I apologize for the D's everywhere. D equals 2 unless said otherwise in this talk. Okay, and you can choose actually discretizations of this domain to be slightly more in slightly more general, but the one which I'm giving, certainly works. So what you do is that you take the set, and then you take all of the points, you scale it up by n, but then you make sure that you do not include any points which are L infinity distance 1/n closer to the boundary. And that makes, the reason for this is that if my domain looks like this, and I have, for instance, a slit like that, then I want this slit to be reproduced also in the scaling, I'm somehow in the discrete structure. In principle, what I need is that these domains are such that the harmonic measure on the boundary of a random walk started from any point inside converges in the scaling limit to the harmonic measure of the continuum domain. Okay, and that this for instance, for these discretizations, this can be proved. Okay, and what's the return? So my random walk runs in the domain until it hits the boundary, then it exits. And now I have to tell you how it returns back. And the way the return mechanism works is that I introduce a boundary vertex to which I'm going to wire all of the boundary edges. Okay, so when the walk exits the domain, it goes to the boundary vertex, and then it chooses any of the edges to the boundary at random and reappears at the boundary. And that just keeps going on and on. Okay, so this way I have a sort of a planar, that's why I wrote it in quotes, because this is not exactly a planar domain necessarily if there are holes in the domain, but it's planar-like for sure, definitely locally. Okay, so let me write Px for the law of the simple random walk on this graph Dn union the boundary vertex, which is started at x. Okay, and then what's the local time? So I will scale the local time, the time parameterizing the local time in a convenient way for the theorems to be true. So LT of Dn, and I'm not gonna write this Dn most of the time, is the actual time of the random walk spent at x, but where the parameterization by t means that you multiply t by the degree of this graph. Okay, and this degree is essentially the volume of the domain Dn times 4, because inside the domain the degree is 4, but the boundary vertex can change it by order of the boundary, and that is important. I cannot ignore that. So that's sort of what you need to do in the argument. Okay, so so here's the first theorem, which tells us what are the scales of the local time. The idea is that I will run the random walk for a multiple of the cover time of this domain of this.
Can I ask a question about the model?
Oh yeah, yeah.
What were the return probabilities once you hit the boundary state? Would you return according to harmonic measure or uniformly?
No. So the way I do it is that I simply consider a graph where I have wired all of the boundary edges to one vertex outside. Okay. And so then this
have the same weight.
What are the weights? Yeah, what are the weights of those edges?
The weights are 1 for all edges.
So uniform. Okay, thanks.
Yeah. So that's right. So you choose the point uniformly. That's right. Okay. So it's a simple random walk on this graph, in the usual sense of the word. Okay. So okay, so there will be one constant which I need to highlight. So here it is. So so I'm going to run the random walk for a multiple of the cover time, which turns out to be proportional to the log n squared, even in the parameterization that I have. So the cover time of this domain should be of order n squared log n squared, but the n squared term is already absorbed in this degree term, which I have here. So my parameterization will only capture the log n squared business. And the assumption is that I have a sequence of positive numbers, such as for some theta, this Tn normalized by log n squared goes to 2 times g times theta, where g is this magic constant, and this magic constant essentially comes from the connection to a Gaussian free field. So at this point, just think of this multiplier as 1 over pi. And the 1 over pi, in fact, is equivalent through a parameterization change to 4 over pi that we saw in the notations prior to that. And again, the choice of the normalization is dictated by a connection with Gaussian free field. Okay, and then the statement is that regardless of where you start the walk in the n, with high probability for the measures of the walk started there, the maximum of the local time behaves like 2g times this quantity. So it's root theta plus 1 squared. And the minimum behaves like root theta minus 1 squared, except when root theta is less or equal than 1, in which case this is simply 0. Okay, so what you see is that as theta increases, the minimum will be 0 until theta hits 1, and then it starts to sort of go along this the curve that's described in the lower line, and then the upper line is written like this. So for theta equals 0, the local time maximum is roughly 2g log n squared, and as I said, that corresponds to the to the statements that we saw in the 2001 paper on the Erdős-Taylor problem.
Sorry, but in the first equation, so Tn is of order n or log n squared?
No, Tn is of order log n squared. I mentioned that because my local time, my actual local time is the actual time multiplied by degree of the domain.
Okay.
And I have to go through this gymnastics because it is important to keep track of the degree of rho, and I cannot quite strip it off in this formula. So I have to sort of do the normalization in 2 stages to make everything correct. Okay, so the Tn, what we will see, Tn is actually also the expected local time, time spent at every vertex, and so that will be exactly why you need 2g theta log n squared, because there are roughly n squared number of vertices. Okay, all right. So with that, here is a statement that we can prove about the late, or what I prefer to call them avoided points. I mean, the word late is not really good because being late means that you've already arrived. It's just that you haven't spent much time on this, and really these are avoided points by the random walk. And we also have other points for which the word late would be in fact more appropriate, but we could not use it because it's already been exploited. Okay, so here's the statement, and the statement says essentially that the scaling limit of suitably normalized point measure associated with the avoided points exists in distribution, and that's all I'm telling you at this point. So the precise statement is that for each lambda between 0 and 1, there exists a random Borel measure, which I will call curly z lambda of d. That measure, we can characterize it, but for now I will only tell you that it charges every open set in D with probability 1. Non-empty open set, I should say. This is non-empty. Okay, so let me non-empty. I always forget to write this. And that also means, because D is empty, D is open, I can set O equal to D. So that also means that the total mass of this measure is in fact finite. Okay, such that if you take theta between 0 and 1, and you take any sequence of times with the asymptotics as I stated, the suitably normalized point measure, so I just take the sum of the delta masses at point x, well, scale the x by n so that everything sits inside the scale domain D, but I only count the points where the local time is actually 0 at the time Tn in my parameterization. Then there's a deterministic sequence for which I have the formula in here. And then when I take this converges in distribution to the z measure, to this curly z measure with parameter square of theta. Okay, so I didn't write this, but of course this gives us a very precise statement about the total number of these avoided points. Because if you evaluate the total mass of this measure, that's permitted by the weak convergence that I have here. So the convergence is with respect to integrals against bounded and continuous functions. And in fact, you can take those functions to be supported on the closure of the set by a tightness argument. And so we can certainly integrate this measure against the function 1 and then count the number of points which are avoided, and that'll tell us that in the asymptotic sense, the number of their number will be this formula times the total mass of the z measure, okay, which we know is positive and finite with probability 1. Okay, so this gives us a far more precise statement, and you can also check that if Tn has this asymptotics, if you normalize the log n away, you see that there's a 2g theta over g log n disappears, so you get an n to the minus theta times 2, and that together this becomes the formula that the 2006 paper has produced, of course, in a slightly different context than this. Okay, so that's the statement for the avoided points, and these measures will keep appearing. So let me talk about other points that we can look at. So the natural thing is to look at a thick and thin points. And remembering that the maximum was given by the maximum of the local time was asymptotic to 2g square root of theta plus 1 squared times log n squared. And the minimum essentially was 2g square root of theta minus 1 squared times log n squared. It turns out that the correct definition of a lambda thick point and the lambda thin point are these formulas. Okay, so the upper formula, you make sense to look at anything for lambda from 0 to 1. And the lower formula, you can go to, I guess, lambda from 0 to square root of theta. I guess I should also make theta lambda less than 1 in this case, because if I don't, then I just don't get any points. Okay, so let me sort of make it less than 1 in here. Okay, and what we should also notice that when lambda is equal to 0, that's this formula gives us 2g root theta squared, that's theta log n squared, and that's a typical value of the local time. So the value lambda equals 0 corresponds sort of to the typical situation. So we expect, in fact, those points to be to contain all but a vanishing fraction of the volume. Okay, so this is the definition of lambda thick and thin points. And there's a certain symmetry between positive and negative lambda, which I'll exploit in the statement. But before then, let me just again show you a couple of simulations. So this is for same run of the random walk on a 1000 by 1000 box, where I take 10 times multiple of the cover time, and I choose lambda fairly small. I choose it plus or minus a 0.1, and I forget which is which. I think I started actually with thick points and thin points. And it's clear that they're complementary to each other. So either you spend little time here, which means either the value is not here, which means that you've actually visited the point more likely, and that's why it appears here, and vice versa. Okay, so these are thick and thin points for the random walk, but now with the boundary mechanism that I described. Okay, and so here's the scaling limit of these. So again, this will look a little bit more dramatic because I need another scale which tells me at which point I'm looking at the cutoff for the thick and thin point. So I still have my Tn to be given by this expression for some theta positive, and then I will take An to be such that An over log n squared has the limit 2g times square root of theta plus lambda squared. Well, lambda can be positive and negative within the bounds I gave you. Okay, I guess, you know, a lambda is still larger than -1 in this case. I should remember to put this in here. Okay. Okay, and then if I look at the set of points where my local time is within a neighborhood of this scale An, and what does it mean to be within a neighborhood? Well, when the fluctuation of it are of order square root of An, and remember that An is log n squared, so this fluctuations are for the square root of this is of order log n, then there is a normalization again, which, you know, has now expressed in terms of the sequences Tn and square root of n, and the limit of this object again exists. So the corresponding measure converges to some multiplier that depends on lambda times the measure z lambda d that I have seen. And now there is an exponential factor which gives me a damping for thick points. That will be a damping upwards. Actually, that tells me, I think, that there is a -1 in here. I apologize. I wanted to eliminate the signs. And okay, so if lambda is positive, then the thick points will be less and less likely when the fluctuations in the upward direction from scale An. When there are thin points, there will be downward damping because lambda is negative in this case. Okay, and if you wonder what is z lambda for lambda negative, it's simply the measure zd lambda for lambda positive. Okay, I'm just using this symmetry. So what can we take from these two? There are these magic measures zd lambda, which describe the scaling limits of the thick points, of the thin points, and also of the avoided points for the random walk. So the question is, what are they? Okay, and this is where the connection to Gaussian free field shows up. Okay, so let me give you again some definitions. So I should say that the situation is of course cooked up so that the geometric setting for the random walk is cooked up so that the connection with the random walk with the Gaussian free field is transparent, and in fact it is really the issue is to go away from that setting and be able to handle, for instance, the torus. Okay, but let's just assume that I have this domain with a boundary vertex. So the boundary vertex can be thought of as a point where you put a boundary condition. So my Gaussian free field will be a Gaussian process indexed by the vertices of Dn, which will vanish at the boundary point. And it's centered, so its mean is 0, and the covariance is given by the green function of the random walk on Dn, which is killed when it hits the boundary vertex. Okay, so the GDN is there's a normalization by the degree of the second argument, and then it's the expected number of visits to y for a random walk started at x prior to its first visits to the boundary vertex. Okay, so you can also think of the green function to be identically 0 at the boundary vertex, which forces the value of the field to be 0 in there. Okay, and then I want to review just two things which will explain the appearance of various constants. So first thing is that if I look at the green function at an interior point of the domain, it admits the following asymptotics. To the leading order, it behaves like a g log n, and that has to do with the recurrence of a random walk. The random walk will return back to x of order a log n times before it actually exits into rho. And in fact, we know that it's going to be g log n times. And then if you want to go beyond the leading order, and that may be somewhat surprising, but that's a fact, that there is basically just a constant C0, which is expressible, but not interesting. And then there's a term which now depends slightly and smoothly on x, which is g times the log of the conformal radius of the point x over n in the continuum domain D. Okay, so this is now, so there's some continuous variation of this order 1 term, and it's expressed in this manner. And then the remaining terms are vanishing, and in fact there's good control as long as you stay away from the boundary. And if you want to look at the values of the green function on the off diagonal, so if you put 2 points x and y, and this formula sort of tacitly assumes that x and y are actually away by order n from each other, but the asymptotics works even closer, then there is in fact a continuum function that this g is asymptotic to, and you simply just take the values of the argument and scale them down. And this continuum function is the green function on the domain D, and that function has a logarithmic singularity on the diagonal, but otherwise it's just a harmonic function in every coordinate and vanishes on the boundary. Okay, so I'm not, there's a formula you can write for this, but these formulas are not so important for me. I just need to know that such things exist because they will appear in the asymptotics. Okay, and so let me now talk a little bit about, so it turns out that the local time asymptotics is closely related to the asymptotics of the thick points of the Gaussian free field. So let me review what this is, and I will just say that some people know, and in fact, I've lectured on this. I lectured on this in 2017 at length in Vancouver. So I've been quite involved in this research. So it starts somehow the study of the maximum of the. So the important thing is to always start with the maximum because it sets the scales. So the maximum of the Gaussian free field on this domain Dn actually has this asymptotics to root g log n. And that's where the constant g, I mean, it starts in here in this leading order asymptotics of the green function and simply goes through various formulas. And in different normalizations, it comes out different. So in the normalization that I have that I normalize by degree, which is the one that I need for the connection with the random walk, g is 1 over 2 pi. If you don't put the degree, then you get a 4 over pi, and that's the one which is responsible for the Euler-Taylor constant in there. Okay, so the maximum goes like 2 root g log n. And then if you want to look at the level sets in between, so you can say, how many points will I have at lambda multiples of the leading order scale of the maximum? And this was actually done by Daviud when he was a graduate student at Stanford. So for all lambda between 0 and 1, the number of such points satisfies this kind of asymptotic formula, which will remind you of the formula for the random walk, where lambda is now here we had a theta in here. So there's clearly a connection between lambda squared and theta, which we will see more explicit a little later. Okay, so this is the formula for the thick points. And again, you can ask, can I go beyond the leading order and calculate this? So I will focus on the second line because that's relevant for the talk. So I actually did this with Oren-Luydor as kind of an offshoot of our work on the maximum, but it turns out to have a life of its own. So you can again associate it with these with the level of points where an is now the running scale, which I will take of the order 2 root g lambda log n. So that's the scale, but you can take that to be any sequence. So you can you take the counting measure of the points, but you also include information about their positions. That's really the idea. And then you normalize by a constant kn, which in this case has the formula e to the minus a n squared, a hat n squared. So this running constant appears in squared. There's a 2g log n in the normalization. So this whole factor is of order log n for the scalings I choose. Then there is an n squared, which essentially comes from the volume. The square root of log n comes from the normalization of the probability density of the value of the individual Gaussian random variable. So this can in fact be verified by the first moment to be tight, first moment calculations. And then the statement is that this measure now, which looks at the level set at scale a hat an for an being asymptotic to lambda times the maximum, converges. And it converges to a structure we have seen before. There's this exponential decay. There's this kind of a Gumbel decay measure. And then there's up to some constant, which I will explain what it is. What I have here is now a fairly explicit measure, which can be constructed by other means. And I will not go into that. And this measure has a name. It's called the Liouville Quantum Gravity measure at parameter lambda, where in my parametrization, the set of parameters for which this measure exists is from 0 to 1. Usually it's taken from 0 to 2, but somehow different parametrization will give you different intervals. So lambda is actually the relative parameter. Okay, and the constant c lambda, I wrote what it is. It's given in terms of g's and the c0 in the asymptotic of the diagonal green function. And then there's some 8 pi's which come from Gaussian calculations. And this is what you get in the result. Okay, so the important thing is that the level sets of the Gaussian free field also have a similar structure as the thick and thin points, where we now know explicitly what this measure. And just as a side remark, I want to say that of course the limit law of the maximum is known very well too, and this goes back to the work of Bramson, Ding, and Zaitouni, who proved that the limit law actually exists. And then in Luydor, we put out a series of papers in which we described the limit law very explicitly and also characterized the local behavior. And essentially, I mean, we know the scaling limit extremely accurately. And it's all thanks to very well known asymptotics of the Gaussian of the green function, and also the fact that the Gaussian free field is a Gibbs measure, is described by a Gibbs measure, and the Gibbs measure has certain domain Markov property that we can exploit. Okay, so how does this connect to the problem? Well, if I want to describe the random walk, the simple random walk parameterized by its actual time, I'm not done yet, and so I just there's a theorem that you need to add to the one that I originally proved with Oren-Luydor, and which is the one where we look at actual Gaussian, where we look at this asymptotic of the field of the point measure, but conditional on the total average of the field to be 0. Okay, so this is, you have a Gaussian process. If we project it onto the subspace on which this sum is 0, so that gives us the conditioning, and then we would like to know the law of this conditional process. And it turns out that the limit takes a similar form, okay, but there is a different measure in here. And so here the statement tells you how to construct this measure, and it's somewhat implicit, because essentially, and this describes how we prove it, is that you can divide a Gaussian, a log normal factor from your Z lambda measure that describes the scaling limit of the thick points to get a new measure, okay? And the log normal factor is independent of the measure. It's spatially dependent through some function delta x. There is an alpha. Alpha was 2 over root g. That's a constant which we saw also in the previous theorem. And then there is a very explicit characterization of what these objects are. So theta d squared is the double integral of the green function. It exists because the green function has only a logarithmic singularity. And the delta x is actually, I wrote a formula, but you can characterize it using PDE. It's a function whose Laplacian is a constant, and that constant is actually the Lebesgue measure of the domain. It's non-negative, and its Laplacian is constant. And for that function and for that Gaussian law, the limit of the conditional point process is described using a similar formula, but the measure z is swapped for the ZD0 measure. That's the measure that I have in there. Okay, so here's a theorem which puts all of this together. So so first, here is a plot of this del function, which as you can see, it has zero boundary condition, and it is kind of this. It's kind of a bump. So it reflects certain spatial inhomogeneity that comes into the problem due to the choice of the. I guess it's due to the choice of the boundary mechanism. Okay, and the theorem which puts all of this together, which is that the limit laws for the avoided thick and thin points, they involve the same family of measures, and these family of measures can be written using this ZD0 measure, where I put some part of this log normal factor back. Okay, I don't put all of it. I just put, if I didn't have the -1 in here, this would just be the Z measure that I hit there, but I don't. I take this -1. Okay, and that's what comes out of the calculation. Okay, I don't expect you to understand it, and I will not explain how this comes about, because the calculations that make this work are actually somewhat unilluminating, even though they're kind of intuitive once you have gone through them, but they're not really, you can kind of communicate them without sitting at a board and explaining things in more detail. So what I will do is that I will look at a simplified version of the problem, which is where we parameterize the random walk by the local time at the boundary vertex, where instead of this ZD0 measure, we get the ZD measure, and that's actually the statement that I proved in the first paper with Yoshihiro, and the second paper is essentially just the extension of this to the parameterization by the total time of the random walk. Okay, so here's the main proof idea, which actually has been kind of useful in many of these papers that I wrote on this, is that you essentially first control tightness. So you have a sequence of point measures on which concentrate on D and maybe D across the real line, and then you prove tightness with respect to the topology of Weil convergence of these measures. And that allows you to extract subsequential weak limits. And then you play games of sorts, depending on the context, that allow you to characterize the law of the subsequential limit uniquely. And once you do that, then you have proved the existence of the limit, and you in fact computed what the limit is very often. Okay, so concerning one, and that's the great feature of looking at the thick points rather than the maximum, is that away from these endpoint values, the tightness is usually verified by just a first moment calculation. So the first step is usually annoying. It requires a computation, but it can be done. So it's really the second step which is non-trivial. And the earlier work on various problems in this field, and I have not really mentioned many of them because the list is long. So it involves Yoshihiro, it involves a lot of people in kind of around Offer-Zeituni and so on. People usually try to control the limit by the second moment calculation. Okay, and that gets you somewhere usually, but not typically to the sharp result. And the reason for that is that the second moment calculation, due to blowups, requires a truncation, and that truncation is the harder the problem you look at. So if you look at the GFF, you can actually still do it. For the local time, well, probably you can do it too, but it's much harder. And it turns out that, for instance, for the local time, there's a very beautiful alternative approach, which was not just exploited by myself, but for instance, in the recent work by Cortines, Louis Dore, and Salietti on the scaling limit of the cover time of a random walk on a homogeneous tree, is that to use a Dynkin isomorphism as the statement is called. So here is the statement. So calling it a Dynkin isomorphism is actually a misquote, because Dynkin isomorphism is a kind of statement of this form. There are a number of versions of this. There's also Eisenbaum isomorphism. The one that we need is the one proved by Eisenman, Caspi, Marcus, Rosen, and Xi. It was probably known to Dynkin, but I don't think I could find it in his work. It's as follows, and it's actually the cleanest of all in a sense. Okay, so there are two things you have to do to state it. So first thing, you have to work in continuous time. So I will write xt, abusing my early notation, for a continuous time, constant speed random walk. The random walk is on this entire graph again. Okay, and I normalize the local time by the degree distribution, and I just realized that I apologize. It's actually I wrote constant speed. I mean variable speed, of course. Okay, so it's a random walk whose rate of transition across every edge is a unit rate. Okay, and so it means that it moves out of the boundary vertex much faster than out of other vertices. Okay, the local time henceforth need to be normalized by the degree of the vertex, which takes care exactly of this effect. And you just integrate the actual time spent by the walk at x from 0 to t. And then the other thing that you have to do is that you have to parametrize the local time by the time at the boundary vertex. And so the way you do it is that you write the tau hat rho of t. That's the first time the local time at the boundary vertex is equal to t. That's the local time, including the boundary vertex time, of course, including this degree normalization. So I really talk about local time, not the actual time. And then I set L hat t to be the quantity L evaluated in this tower of t. Okay, so this quantity has the property that LT of rho, L hat of t of rho, is equal to t. And in fact, this is true in expectation at every vertex. At every vertex now, the local time, the expected local time, is exactly equal to t. And that's already a special feature of this representation. In the previous representation, that was true in the leading order, but there were fluctuations. At this point, the expectation was equal to t modulo lower order terms. The fluctuations are always there. And then the local time, but this is now true explicitly for all vertices. And at rho, it's equal pointwise by the choice that I make. Okay, and this second Reid-Knight theorem is, the statement is as follows, is that there exists a coupling of the local time parametrized by the time at the boundary vertex and two copies of the Gaussian free field H and H tilde. Now I write it on a V, and V in this case can be any finite graph. We will take V to be dn, of course, in this, but I write it just for simplicity like that, such that the one of the copies is independent of L hat t. So the objects are independent. The other copy will, of course, depend on both of them. And there's a pointwise identity that for all x in V, the local time plus half of the first Gaussian free field is 1/2 of the second Gaussian free field, which is shifted by a square root of 2t. And this is true for every fixed t. And the way you prove it is that you, in fact, prove first that this is true in distribution, and then you invoke some basic facts about essentially abstract nonsense facts from probability to take care of, to reconstruct this in terms of a pointwise identity. And the key point being here is that I have only squares here. So this identity does not track the sign of these quantities. And that's something that you have to worry about when you're trying to prove this as a pointwise identity. Okay, so the important thing is that I have a Gaussian free field, square it, take 1/2, add to the local time. And then this whole object can be regarded essentially as another copy of a Gaussian free field, modulo this shift. Okay, that's very important for the story. Okay, so what's the idea in here? Okay, so let's assume that I want to look at thick points, okay, or points where local time is of order an, okay, or it's an plus small order. Okay, now the idea is that if I somehow can ignore this field on the left-hand side, okay, which means that if I can pretend that L hat is essentially equal to the right-hand side, at least at the points where I care for, this allows me to solve the equality. So I have LT is now approximately an is now therefore approximately this quantity. This is now a calculation. So H tilde therefore has to be either square root of 2n minus square root of Tn, or it has to be minus square root of 2an minus square root of T to Tn. Okay. Now, if an goes to infinity, this number in absolute value is much larger than that number in absolute value, which means that this type of solutions would look at the level set, which is farther away from the typical value, which is as close to 0, than this guy. So at least for thick and thin points, it turns out that this is the dominating term in the solution. So that would tell me that if I want to look at the local time being of that order, that should roughly have the same kind of distribution as when the Gaussian free field is roughly equal to this quantity. Okay, so if I write a hat n for this quantity on the right, then I can do a little calculation, and that will sort of ex post justify why I defined my thick points in this form, because this formula has been cooked up so that everything works. So if Tn is 2g theta log n squared and an is 2g times root theta plus lambda squared log n squared, you take all of the square roots, they eliminate this, and the theta term subtracts from here. I mean, actually, square root of theta term subtracts from here, and we end up that an is asymptotic to this formula. And that's exactly the thick points of the simple random walk. Of the Gaussian free field, of which my work with Orr and Ludor is applicable. Okay, so that's roughly the basic idea: is that if I can ignore the Gaussian free field on the left-hand side, then I would be in business, and I would get this formula. Okay, it gets slightly different for the situation where the local time itself is small. So if an is of order unity, then of course this term itself is the same as this term itself. And in this the two solutions become, they blend together. And in this case, you're looking at H tilde being essentially square root of T to Tn, and that's still a value that grows linearly in n. So that still corresponds to a thick point of a Gaussian free field, but you have to sort of treat this differently. So that's actually what I'm going to do for the rest of the talk. I'm going to explain roughly, to give you the flavor of the idea, because the calculations get really complicated, what you do to actually extract the results for the avoided points, which I consider to be perhaps the most interesting of all of these. Okay, so as I said, we need to, in order to control the avoided points, we need to actually introduce slight relaxation of being avoided. We call this light points. I mean, that's what the word late points should have been referred to, because those are the points which are typically visited only a few times, and that's well, okay. So those are the points where the local time is actually of order unity. So if I would like to describe the scaling limit of such points, what I would do is that I would do same kind of a game as before. I would consider a point measure where I record the position of a point, and then I record the value of the local time. But because I expect this measure to be integrated only against compactly supported functions in the second variable, then I don't put any normalization. And that essentially forces the contributions to be coming from the points where the local time is of order unity. Okay, so this is the light point measure. Okay, so you go through the game as before, is that you calculate essentially explicitly, because the probability that a point is avoided can be calculated explicitly, and being light and avoided is not that different from each other. So you can calculate the expected size of this set, and it turns out that that has an asymptotics, which is this formula W hat n, and W hat n was the formula where you wrote n squared times e to the minus tn over g log n. Okay, so this is an explicit formula in terms of the tn sequence that parameterizes the time. So that tells us that these measures, in fact, are tight. So we can look at the subsequential scaling limit. So assume that you have a subsequence nk along which this theta n tends in law to theta. Okay, what does that mean? It means that if I integrate it against any compactly supported function in both variables, where the compact support, of course, in the first variable is kind of moot because the measure is compactly supported by kind of the choice. But in the second variable, it's highly non-trivial. Then the integrals of this measure against the function against this measure converges in law to the corresponding integral of this. Okay, so suppose that takes place. Okay, and in order to control the effect of the field on the left-hand side in this Dynkin isomorphism formula, I simply introduce the measure which keeps track of that term as well. So I take the same measure in here and I extend it by a third coordinate, where in the third coordinate I keep track of this h. Okay, so when effectively will this triple product have a non-trivial contribution under an integral against a compactly supported function now in 3 variables? Well, only if, well, x can be anything, of course, but L has to be of order unity, and also h has to be of order unity in here. Okay, so h being of order unity, that's a pretty stringent requirement because h has a variance log n, hx is variance log n, so it will typically fluctuate on the scale squared of log n. Okay, so the probability that it's of order unity is roughly 1 over squared of log n. So what I'm doing is that I'm looking at these points and I'm thinning the process by those values of the Gaussian free field, where the Gaussian free field is of order unity, and that itself has probability 1 over squared of n. Of course, the trouble is that Gaussian free field is not an IAD process, so this is not really a thinning. It's actually very far from an IAD process because correlations decay. There's a logarithmic scaling of the correlations, and so this is why this is a very non-trivial lemma to prove. But it turns out that the thinning still works, and that's kind of the magic of this proof, is that if I write it as this measure, and I of course need to multiply the result by the square of log n to account for this thinning probability. And once this theta n converges to theta, sorry, this theta dn converges to theta d, then this thinned measure converges to a product of theta d with a suitably normalized Lebesgue measure. And the Lebesgue measure comes from the fact that the probability density of hx is nearly constant when hx varies of order unity. And the normalization of that measure can be written as 2 pi g. Okay, where g is the variance of hx. The 2 pi g, in fact, in my normalization is 1, but I write it so to keep track of the role of g in this formula. Okay, so this is a very key lemma, because that, once I have this, then I can use it to derive a convolution identity that every subsequential limit of these measures has to satisfy. Okay, so recall that L hat n plus 1/2 squared is equal to a Gaussian free field with this shift in here. Okay, so under this measure, if I look at this measure, and I integrate it against the function which only depends on the combination L plus 1/2 h squared, then I can use the distribution in norm, and then I can replace this by a copy of a Gaussian free field. Okay, this measure. And if I do that, then of course the limit of this quantity by the argument that I gave you, that essentially is if both L and h is small, if L plus 1/2 h squared is small, both have to be small, which means that also this term has to be small, which means that h tilde is very close to order unity from -2 Tn. That's exactly within the purview of the scaling limit of the level sets of a Gaussian free field. So as a consequence of that, you get that every subsequential limit of these processes satisfies a certain convolution identity. If I give you a function f of these variables and I integrate out h against the Lebesgue measure, this normalized Lebesgue measure. So I call this fxl because L is still a parameter in this. Then the integral of this limit measure against this this kind of processed function convolved with Lebesgue function has a scaling limit, and that scaling limit is the one for the Gaussian free field for lambda being squared of theta. Okay, and this combination now in the argument is replaced by h squared over 2, and that's because we're looking now at the fluctuations away from the square root of Tn. Okay, so that's an identity. I'm not expecting you that you can follow all of these calculations, but this is sort of a prototypical lemma that comes out of this identity, is that you assume the subsequential convergence, you apply the Dynkin isomorphism, and you get a convolution identity. And now the question is, this is true now for every compactly supported function. The question is, can I extract the law of eta from this? And the answer is yes, and it requires some games around the Laplace transform. It actually is not that hard for this example. It's pretty hard for the thick and thin points. Okay, so the bottom line is that the convolution identity can be solved, and that shows me that this light point measure converges to a measure of this form, where in here I already have the z measure corresponding to the scaling limit of the level sets of a Gaussian free field, and in the second coordinate I have some measure which is supported on the positive reals, and that measure has a delta mass at 0, and it has some continuous part with respect to h. Okay, and then essentially what you do is that you say, well, since the light point measure also contains the avoided set measure, so if I now integrate it against the function, which in the second variable is supported very close to 0, this continuous part will contribute almost nothing, and most of the contribution will come from the point being actually avoided, and that's exactly what happens. So setting looking at the value of this measure just at the origin then gives you the statement is that the avoided point measure parametrized by the local time at the boundary point has a scaling limit, and that's this quantity. Okay, so we have now the law of the avoided points in this parametrization. Okay, so this is essentially my last slide. I hope that it's okay that I'm a little over time. Okay, so now come 2 steps, and the 2 steps amount to a 50-page paper. So I don't want to put it lightly, but essentially that's what you have to do, is that you need to do it 2 steps. So first thing is that you need to go to the time parametrization by the actual time of the continuous time walk. Okay, and that's that requires work, and I will say a few words about this. And then once you're done with that, then you need to reduce the continuous time walk to a discrete time random walk, which again has some technicalities in various cases. So in the reduction to the actual time of the walk, it turns out that what you have to do is that you look at the fluctuations of the total time at a given time at rho. So if you know that your random walk spent a given time at rho, your total time is not a fixed random variable. It actually is. It has the leading order that you expect. That corresponds to simply, if the time at rho, local time at rho is t, then you expect the total time to be of order t times the total degree of the graph. That's kind of an expectation calculation, but there'll be fluctuations, and the fluctuations will essentially be Gaussian, and that's the whole point, will be Gaussian around that mean. And so if you scale those fluctuations by log n, it turns out that you get a Gaussian random variable, and that Gaussian random variable has exactly the distribution of that y that appeared in the conversion of one z measure to the other z measure. Okay, and then you can again look at the Dynkin formula, and I'm not writing this calculation anymore, but that's actually what you do, is that you can look at what does it mean to fix the local time precisely to fix that fluctuations. And it turns out that's essentially, that's on the left-hand side of the formula, that on the right-hand side, that's tantamount to fixing the value of this h tilde x. Okay. And now we want to look at the situation where the fluctuations is 0, because essentially our parameterization is such that we're trying to parameterize the total time by what it would be in expectation if the local time at the boundary is Tn, at the boundary vertex is Tn. And so we need to fix this total time, this Gaussian free field to 0. And then you sort of process this through a conditioning argument, and that's the reason why this measure appears. Okay. However, there are some corrections which come from the conversion, which come from the fact that your normalization itself will depend on it depends on Tn. So if you now go from the fixed value of the local time at the boundary vertex to fixed total time value, you allow the boundary vertex value to fluctuate, and that brings about one more occurrence of this random effect. And that's responsible exactly for this -1 expression in here. Oh, I apologize for this delta x expression in here. That's no, I'm saying that this -1 expression. Okay. Okay, the bottom line is that you do not get back your z measure, but you get a measure with this kind of logarithmic prefactor. And understanding the role of this normalization is actually quite important when you look beyond, and I will mention this on my very last slide. Okay, so once this is done, then you have to reduce from the continuous time to discrete random walk, and this actually has essentially no effect on the avoided points or light points, but it has a non-trivial. Well, on the light points, it has the effect that your measure is continuous for the light points, and for the discrete discrete time walk, it will be a discrete, but then there's just a Laplace transform calculation. But there is in fact a non-trivial fluctuation term which appears for the thick points, and that's because if you can think of, if you know how many times you visited a given vertex, and now you add up an exponential, independent exponential with this, then of course in the mean they will be equal, but the exponentials will produce an additional Gaussian term which is going to change the fluctuations by an amount. And you can, again, through a kind of convolution identities, identify what the measure would be for the discrete time process if you know what it is for the continuous time process. Okay, I've spared you all of those details, but it can be done. Okay, so I'll just mention what is there to do and what is in fact in the works and what is our plan. So the first thing is that I would actually really resolve the problem of the 2006 paper of Dembo, Perez, Rosen, and Zaitouni, where we are looking at either the torus boundary condition or generally a reflecting boundary condition if there is in fact a boundary. So I would like to take the domain Dn, but not introduce the boundary mechanism, but every time the walk hits the boundary, it's reflected. So it's not allowed to go outside. And the walk then needs to, so then you don't have a boundary vertex to play this game with, and you have to use the starting point of the walk. And we in fact know what happens if you parameterize the measure using the local time, using the local time at the starting point. And it turns out that you pick up an additional random factor which no longer has a scaling limit, and you have to deal with this. And this is in fact a known problem when we look at the cover time of this cover time scaling limits, which is another question I would like to look at. Well, okay, so this is for the avoided points. And then there's another one. I've avoided all these boundary values. So even the most visited point has not quite been addressed in this game. But based on a conversation that I had with Oren Luidor when he kind of surprisingly visited me in November, we think that we can do it. And the limit in this case, of course, will be the critical Liouville quantum gravity, and there'll be a Poissonian statistic. So something very familiar from the Gaussian free field picture persists in here. And in fact, in a sense, the local time is very closely described by Gaussian free field, except that there are notable corrections that you have to take into account. Okay, and then there's a kind of a big time, much larger problem to look at, which is the scaling limit of the cover time in all of these contexts, which requires literally looking at the minimum of the local time at a time when there's only a few points left to cover. Okay, so I finish here, and thank you for your attention.
Thank you, Marek.
Sure.
Any questions?
So first, concerning the last point, so the last slide, if you just have reflecting boundary conditions, so what is, so you still have a similar version of the Dynkin isomorphism?
Except that you have to do it now. Yeah, well, you have to parameterize. For the Dynkin isomorphism, you need to parameterize by a local time at one vertex. So the natural thing, and you, since you're starting at a given point, it's natural to use the starting point.
Yes.
Okay. The trouble being is that if the corresponding Gaussian free field is now 0 at this point, but it has a free boundary condition.
Okay.
That field you can think of, you take the 0 average field on the domain everywhere, and you subtract the value at the starting point. That has the same law. And as a consequence, that field will enjoy an additional fluctuation, which comes from the value of this 0 mean field at the starting point, which is of order squared of log n. And that creates that wreaks havoc in the formulas, I can tell you.
Mm-hmm.
Essentially because this term, that term appears in all sorts of products with terms which are themselves of order log n. So it produces a factor of order log n to the 3/2, and which is more of a random. And so when you deal with it, you can imagine that terms proportional to log you can probably beat by normalization. The log n squared you explicate, but now you have this kind of intermediate term, and that's exactly what happens. So the right normalization for the measure involves exponential of this term divided by log n, which is itself of order squared of log n. And in that sense, the limit still exists.
Right.
That limit depends on some random quantity, which depends on the Gaussian free field, which in itself is coupled to the random walk. So now you have to go through your reductions backwards and keep track of what happens each time you reduce.
Okay.
Yeah.
So if you try to use your result and somehow use the machinery of soft local times, do you get some non-trivial statements about reflecting boundary condition?
So are you okay? So I'm confused by the word soft. What do you mean by soft?
I think that's the name of this method that somehow allows you to get stochastic domination in both directions between a regular random walk and between having a random interlacement from the boundary.
Okay, so I know that I don't know the name of this method, but it's I know you can certainly do stochastic domination in one direction, right? Always. Yeah, okay. I haven't. It's a good idea. We haven't looked at that.
Well, I mean, you get very precise statements. So if you only get things up to domination, they would be a weaker statement.
Mm-hmm. Yeah. Well, I haven't tried that, so I can't pronounce any judgment. So the fact is that you can use just so even if you just use, there's one domination argument which has been used, which is where you simply neglect the term on the left-hand side of the Dynkin isomorphism. That's sort of the easiest domination argument. So your L is bounded, dominated by Gaussian free field, and that gives you one-way direction to various estimates, but it does not really get you further. So even proving tightness using this argument is not completely straightforward. So you can prove tightness, for instance, for the thick points using this argument, but for the thin points, you're already in trouble because your inequalities go in the wrong direction.
Second term is significant.
Yeah. Well, the second term is actually not significant. That's the whole point of my talk.
Okay.
But it does not, that doesn't come for free. I mean, that's exactly what you have to get around. Okay.
Yeah.
So so we have a strategy which I think will certainly work for the parameterization by the local time at the starting point. And then it's of course a matter of your taste whether you take that to be a natural result or whether you would prefer to have the full picture, which may be so horrible that you actually are not able to sort of process it anyway. Okay. So that's why the third paper is not really written, because we're kind of debating what's the correct philosophical statement we want to do, because we can certainly do the parameterization by the local time at the starting point with work. I mean, it doesn't come for free, but we can do that.
Yeah, I see. That sounds like the better approach to me.
Then inequality.
Omer, should we close the recording?
Yes, let's do that.